Hello, welcome back. The title of this lesson is called Static and Kinetic Friction Forces, or Frictional Forces, and this is part one. So, title sounds a little confusing or a little intimidating, static and kinetic friction. What is all that about? So we're going to dive into the concept of friction in this lesson. And we're rapidly going to figure out or discuss that there's really two regimes of friction that we need to talk about, right? And we all have everyday experience with it, so it's stuff that you're going to immediately understand intuitively. But we want to go beyond just intuitively understanding it, and we want to be able to calculate the frictional force that we're dealing with most objects that we're pushing or pulling around in terms of physics. Because remember, how an object moves really depends on what forces are acting on the object, right? And so we all know that, F equals ma. Well, one of the biggest forces that we haven't talked about yet is the everyday frictional force. Everything we do, almost everything we do, with the exception of maybe a spacecraft in deep space, has frictional forces. Airplanes, when they fly through the air, they're encountering all that wind resistance that causes friction, and it tries to slow the airplane down. That's a frictional force, right? We call it drag in an airplane, right? But even just pushing a box across the floor, sliding on the carpet, it has a resistance to us trying to push it. That's a frictional force. Even an ice skater, the contact point of the ice skate with the ice, a very small blade, there is a small amount of friction there. Of course, an ice skater or a hockey puck can go very, very far because the friction is very low, but it is still present, and the hockey puck will eventually slow down and come to rest, and the ice skater will eventually slow down and come to rest. It's all because of friction. Any motor that is rotating, any engine with a piston, any jet with a turbine that is spinning and air coming through it, they're all encountering friction. So friction is one of those things that we really cannot get away from, because anything mechanical that we build that rubs on something, even if it's rubbing on air like an airplane wing, is going to tend to slow the system down. I said the main exception to that might be deep space travel when there's no air, right? And you just push something and it goes forever. But even in deep space, there's a small amount of friction because there are atoms in space, even in very deep space. It's just not very many of them. So really, you can never, ever really get away from the concept of friction. All right, now let's take it from deep space down to Earth and let's talk about friction. We're going to do a little bit of a discussion of what it is, bring it to everyday experience, and then we'll draw a lot of pictures to talk about it. Now, I want you to picture yourself in a big room that has carpet on the floor, okay? And then maybe another room next door that's an ice skating rink. So two different situations. Which one is going to have more friction? We all know the carpet, if we're pushing an object sliding on the carpet, it's going to have more friction. And if we have the same object and we put it on the ice rink, let's say we're pushing a giant box or something, just a rectangular bottom box, you're pushing it. If we push it on the ice skating rink, it's going to slide easier. We have lower friction on the ice. We have higher friction on the carpet. So we know that since the object is the same, the box is the same, and we know that if we can push with the same force, the behavior is different depending on the material. So whatever we talk about when it comes to friction, we have to have the equations take into account the material properties, right? Because carpet's going to have more friction than ice, or whatever. Pick your sandpaper. It will have more friction than a smooth piece of glass, which will have lower amount of friction. So the material is very important for figuring out what the frictional force will do. Secondly, let's move back to our example in the carpet, where we're trying to push a box on the carpet. I want you to actually do this. Grab a big heavy box that you're able to slide, but I want you to push on it. Don't tip it over. Don't crush anybody, okay? I'm not asking anybody to do anything dangerous. I'm just saying push on it, but don't push too hard. Then what happens? We all know that feeling of pushing on something where it's sitting on a carpet and it doesn't move initially. We're pushing, but yet the contact forces with the ground is sort of preventing it from moving at all. So we push a little more. And again, maybe it's not barely moving, but not really moving. It's still resisting. In other words, when we push on objects when they're in contact with the ground, they don't move at all initially until we push past some sort of critical force. Once we pass the critical force, then it kind of unlocks from the friction and it begins to move. And once it is actually moving, then to continue to move it, it actually is not as hard to keep pushing it and to keep it moving. So it's almost as if the objects, when they're sitting on the ground, they're kind of locked in place, and we have to push with some sort of like minimum kind of like force to overcome that initial friction. And then when it starts moving, it's like easier to keep moving, sort of. So that's what we're going to talk about today. It's called static friction, and it's called kinetic friction. That's why the title of the lesson is Static and Kinetic Frictional Forces, because there's two kinds of frictional forces. The static frictional force is when I push on a box and it doesn't yet move. In other words, there is friction with the carpet, but the object has not yet moved yet. So I push more, and I push more, and I push more, but as long as it's not moving, it's called static friction. Then, whenever we finally dislodge the object and it begins to slide and we continue running behind it, pushing it, we feel the friction, but it's moving. We call that kinetic friction. And those are two different regimes. Now, what I'm going to do on the board, the first thing I'm doing on the board is I'm going to write the equations of static and kinetic friction down. But I'm not going to explain them too much because I'm just getting them down there in the beginning so you have them in the back of your mind, okay? But really, we need to talk about it. I need to draw some pictures. I need to draw some graphs for you to really understand how these equations work. And once you get it, then we have a problem where we'll apply it. And we have many more problems beyond this where we will continue applying the frictional forces. So we have two main regimes. We have something called the static frictional force, frictional force. And that equation looks very complex, but it's really not complex. Some force, which is static, the S there means static frictional force, is less than or equal to the Greek letter mu sub s, because it's a static frictional coefficient, which we'll talk about in a second, multiplied by the normal force. Now, this is a little bit weird to write this equation right now because I haven't really drawn a picture yet. But basically what this equation is saying is that the static frictional force, it has to be less than or equal to some maximum value. Remember I said there was like a critical value. When you push just enough, you can unlock it and it starts moving. Well, up until that point, when you push on it, the box is pushing back on you with a frictional force, essentially. And so the frictional force can rise up to a maximum value, but once you get past that maximum value, then the box begins to move, and it's no longer in static friction anymore. It's in kinetic friction. So the frictional force in the static case is always less than or equal to a maximum number. Now, what's this maximum number? Well, the normal force is the, remember, when you have an object sitting on the ground, you have the weight of the object acting down, and the reaction force is the ground is pushing up. So that's the normal force. So it's basically the same value, but in the other direction as the weight of the object. So this is almost like the weight of the object times this, right? And this number is what we call the coefficient of static friction. So this is where we fold in the different properties of the surface. We said ice has a low friction and carpet has a higher friction. So for ice, this number would be close to 0, the coefficient of static friction, and for carpet, it will be much, much higher. But notice that whatever this number is, this is just the material properties. You're multiplying essentially by the weight of the object. The normal force is the same value as the weight of the object. So what we're saying is that the static frictional force is a number, that this is a resistance to motion, that is a force in newtons, that is less than or equal to a maximum value, but the maximum value depends on the weight of the object, because this is the normal force, which is up, where weight acts down. The weight of the object times some material properties, right? And you all know that if you put an object on the carpet and it's very, very heavy, where the normal force pushing up from the ground is very, very big, you know that there's going to be a much higher frictional force. So the frictional force should go up as the weight of the object, or the normal force of the ground acting up on the object, is higher. That's why we have the normal force here, because heavier objects have more friction, right? And of course, then it's multiplied by either on ice or on carpet. That's going to change the frictional force as well. So if you have a very heavy object, but on ice, then the frictional force can still be low because this is going to be close to 0 and so on. So it takes both into account, the weight of the object and whatever the object is sitting on. That coefficient of static friction is going to depend on that, okay? Now, let me move on to the next case, which is the kinetic friction. So I'm going to call it kinetic friction. force, right? Kinetic frictional force. And it might be a good idea to go ahead and just draw a quick picture here, right? Let's say we have a box, right, sitting on the ground. And what's basically going on is you have some rope or something attached right here. And I'm pulling to the right with some force or some tension T. I'm pulling on a rope, let's say. Now, the box has a weight, which is gravity pulling down on the box. But the box is sitting on the ground, and so the reaction force is that the ground is pushing up on the box. So this is the weight here, and then acting up, which is equal and opposite of the weight, is what we call the normal force. That's acting up here. And so every time we start pulling on this thing in this direction, the frictional force is always acting in the opposite direction, and we call it F. In this case, we can call it Fs for the static frictional force. So as I start pulling on the object, the static frictional force will get bigger and bigger and bigger to counteract my pull, and so the object doesn't move. You see? Because remember, when you put an object on the ground and you start pushing or you start pulling, initially, if you cannot overcome the static friction, it doesn't move. Why doesn't it move? Because Newton's law says things don't accelerate if all the forces are balanced. So what's going on is as I pull on it, there's a force here, a frictional force that is pulling in the other direction or that resists the motion, so that these two are equal and opposite, and so the object doesn't move. Because this is equal to this and this is equal to this, object doesn't move. But if I pull a little bit more than the maximum value allowed by static friction, which I can calculate based on the weight of the object and the coefficient of static friction, if I pull 1 Newton more than that, the object begins to move. And then you're no longer in static friction anymore. You are in kinetic friction. That's what we have here. Now, the kinetic frictional force is called F sub k for the frictional force due to kinetic motion, right? And that is another Greek letter mu, but this one's called k, again, times the normal force. So the equations look the same. The only difference is when an object is stationary, we have a static frictional force, a static coefficient of static friction. And when an object is actually already moving, we have a different coefficient. We call the coefficient of kinetic friction. But in both cases, the frictional force is equal to this coefficient that is basically the object you're sitting on, carpet or ice, multiplied by the normal force, which is the weight of the object. So no matter if it's static friction or kinetic friction after you're moving, the weight of the object, the normal force, the weight of the object is the dominating factor really that governs how much frictional force you have, right? And then of course, once you start moving and you kind of break it loose of its initial kind of being stuck on the carpet, then we all know it's a little bit easier to keep it moving once you start it moving. And there is a new and different coefficient. This one is called kinetic friction. Usually it's lower, a smaller value than the static friction number there, but it's a constant. Notice that this one is an equal sign and this one is a less than or equal sign. We're going to talk about why in a second. I don't want to get too far into the weeds right now as to why one of them is an equal sign and one of them is not, because we need to draw a couple of pictures. But basically, once the object is moving, the frictional force is constant. You just calculate what it is. What is the weight of the object? What is the coefficient of kinetic friction? And there you go. Before the object starts moving, there's a little different interaction that we need to talk about, which I've already verbalized to you, but I need to draw some pictures. So this is the punchline. You can solve your physics problems by calculating these frictional forces, and then you treat the frictional force just like any other force in Newton's law to figure out how the object is going to move. But let's dive a little bit deeper. Let's go back here to the first board, and let's talk about the idea, just starting over again, even though we've already talked about it here. There's basically two regimes when we deal with friction, two regimes. Right? We have the box. In this case, we're talking about a box on the carpet not moving. And we have the box moving. Right? There's a little bit of overlap in what I'm about to say based on what I already wrote. That's okay. Overlap is good because it gives you reinforcement. When the box is not moving, this is called static friction. Static means not moving. And when the box is moving, this is called kinetic. The word kinetic means to move, right? And we're going to redraw our picture over here. We're going to draw several of them in sequence, actually, to get a really good feel for what this is doing. So what I'm going to do is I'm going to draw a box right here. It's not going to be too big. It's not going to be too small. But here is a box, and this box is sitting on the ground. And what forces are acting on this box? Well, the box has a force of gravity. The Earth is pulling on this box down with some weight. And because it's cramming itself into the ground has a reaction force acting up on this object, equal and opposite magnitude, but this is called the normal force. So in these equations, which I've already written down and we'll talk about more later, we put the normal force in here, which is exactly the same number as the weight of the object, but the normal force is acting up. That's why we put the normal force in there instead of the weight, because technically the weight is acting down, and technically the weight is a negative number because down is negative. But we don't want all of our frictional forces to, it depends on how you want to treat the signs. Typically we're going to draw a picture, we're going to draw the arrows, and we're going to know which direction the signs are. But traditionally you could put W in here for the weight, and there's nothing really wrong with it, but typically we put the normal force in for essentially for the weight of the object, because the normal force is positive. And so you'll get a frictional force which is positive in your calculations for what the frictional force is. All right, and then over here to the right, we have some rope or something. We can just pull on this thing with some tension T, like this. And we already basically wrote this down over here, but we're going to draw a bunch of pictures in sequence to make sure we understand. Now this box initially is not moving, because when we push or pull on a box, just with a small push, it doesn't move. And that means that all of the forces have to be balanced on the box. Otherwise it would move. So when I push on it or I pull on it, the frictional force that arises must be exactly counterbalancing whatever force I'm applying. And you might say, where does that force come from? The box doesn't have hands to push back. Well, no, but the box has atoms. The box has electrostatic attraction between atoms, and also parts of the floor are catching onto the underside of the box, and that's resisting its motion. That's where the counterforce comes from. It comes from the actual interaction of the bottom of the box with the carpet or whatever it is you're pulling on. But in this case, notice my arrow is this long. So what I'm going to do is I'm going to draw this arrow the same length. That's on purpose. This is the frictional static force. I'm trying to draw them the same length to show you that this frictional force that has popped up here as a counterbalance to this one is exactly the same length. So this box is not going to move, because even though I've pulled on it, the frictional force is equal and opposite, and they're both acting on the box. And so the box up and down forces, left and right forces are all balanced, so the box isn't going to move. All right. Now let's take a closer look at maybe this part right here where the actual box meets the ground. Let's draw that over here. Well, the ground, if you could zoom in on the carpet or the ice or whatever it is you would be looking at there, the ground would actually be very jagged. It would look something like this. So this is the ground, right? Like this. And the box that I'm sliding, you know, there's a flat surface and then a corner right here, but the box is not smooth. The box has all this jaggedness too, and also on the side like this. Now, can you see how, and this up here, this is the box. As I pull the box to the right with some force or tension T through a rope, then all these little hooks that are in the bottom of the box, you know, because it's irregular and jagged, are going to catch on all of these little peaks that are down below, and that's essentially what the frictional force is. It's the two materials coming into contact with each other. You know, because it's not a totally smooth, flat surface, of course, things are going to catch, and that's going to slow down your pull, and that's what manifests as a frictional force, because it's microscopic. Now on ice, something very smooth, or glass, then you would zoom in on this and it would be much, much smoother. But believe me, I've looked at a glass under an electron microscope. I've looked at a razor blade, a very smooth piece of metal under an electron microscope, and even very smooth things like that have these jagged, crazy peaks under an electron microscope. It's very hard. Even the tip of a razor blade, very sharp knife, right, has all these pits in it and score marks, and the microscopic world is just incredible. We just don't see it, okay? But the point is something like carpet or sandpaper would have these enormous hills and valleys, you know, whereas glass would still have some up and down jaggedness to it, but not as much, and ice wouldn't either, okay? And so this jaggedness of these material interface here is going to come into these equations with these coefficients of static friction and kinetic friction. As I mentioned, ice would have a very small number here for both of them, and sandpaper or carpet or grass or anything like that would have a bigger a coefficient of static friction, which would yield a higher frictional force, okay? Now let's continue this thought experiment here. Let's draw the same exact situation again, but what I'll do is, I'll draw it in the same place, at least this next time. I'll put it right here. And there's a normal force here, and there's a weight here, right? And there is a tension here. But instead of that I'm pulling on this rope, but instead of pulling this much, let's pull a little bit harder. That means the arrow is a little bit longer. But if the object is still not moving, then the frictional force must be equal and opposite in the opposite. I'm trying to draw these the same length. I'm not doing a great job. But the tension here and the static frictional force, if the object is still not moving, even after I pull a little bit harder, then what it means is the static frictional force must be a little bit bigger in this case than it was in the first case. So in other words, the frictional force gets a little bigger here to counteract the bigger pull, right? So initially, if I'm pulling a little bit, then the two materials rubbing it doesn't have to push back as much because I'm not pulling as much. If I pull more, then of course these hooks, they grab each other, and then the impact between the two and the catching that's going on is greater there, and that shows up as a greater frictional force. The harder I pull, the harder the reaction force that's really going on behind the scenes. And if I do it again, you can see what's going to happen here. Let me exaggerate it here. You have the weight of this box. You have the normal force of this box, right? And let's say that I pull, really, really hard here. I may run out of space here, but basically what's going to happen is I'm going to have a very large static frictional force. So as I start with a small pull, I get a small static frictional force. As I get a slightly bigger pull, I have a slightly bigger static frictional force, but yet everything is still balanced. Box does not move. Box does not move. Here, I pull very, very, very hard, right at the breaking point, right when it's just barely, barely, barely able to hold on. It's about to move. The static frictional force, again, is balanced here. So in all three of these cases, the box is not moving, right? And so what that means is what's going on here is that what you get to a point is that when I pull, I get a frictional force. When I pull harder, I get a slightly bigger static frictional force. Eventually, I pull right to the point, or I push right to the point where the box is just about to move, but I'm still on the safe side. It hasn't moved yet, but I'm 1 nanonewton, one tiny hair's breadth away from getting it to move. Then what's going to happen is this frictional force reaches a maximum value. I wish I didn't run out of room there. Sorry about that. Maximum value. A maximum value above which the box will begin to move, but below which it's able to barely hang on. Microscopically, what's going on is you pull with just enough force to get it to rub at all of these places. And maybe what's happening microscopically is some of these peaks and troughs of the, if you're on sandpaper or something, are just about to collapse, and then the thing is about to be able to roll over it. Or maybe you're pulling and it's just you're basically moving it out of the troughs, like maybe the horizontal pull lifts it. It hits the peaks here and kind of lifts itself out, and it's just about to slide across the top of them, all right? But until that point, it's able to resist your pull exactly Newton for Newton. Pull a little bit more, then a frictional force a little bit higher, a little bit higher, a little bit higher, a little bit higher, until the breaking point is reached. That is the maximum static frictional force. 1 little Newton or nanonewton higher than that, then the box begins to move. That is why the static frictional force equation has a less than or equal sign to it, because the static frictional force is something that can change. It's not just a fixed number. What basically is happening is when the object isn't moving, the static frictional force just gets bigger and bigger to counteract whatever force it is. But it cannot get bigger than this number. It has to be smaller or equal to this number, and this number is the weight of the object, the normal force, times whatever the coefficient of static friction is. That is the maximum value you can push or pull without breaking it free and it beginning to move. Okay, let's talk about what happens when it begins to move. So we have all of these drawings here, and on this board, we're going to talk about kinetic friction. What happens when it begins to move? Kinetic friction. All right. So let's draw our box one more time. But in this case, what we're going to do is draw the situation in which case we pull just enough so that it's broken free. And now we're sliding it across the ground. This box still has a weight. This box still has a normal force, which is exactly equal and opposite of its weight, right? But now this rope, I am pulling with a tension that is high enough to overcome, notice it's a very big arrow here, to overcome the static frictional force. Notice from your everyday experience, heavy object on the ground, you push really hard to get moving, then it breaks free, and as soon as it breaks free, it almost feels like it's easier to push it. In other words, you have to push enough to almost lift it out of the catching that is going on here. That's why you have to push a little bit more to almost lift it out of all the catching that's going on and kind of get it on top of that. And once it's sliding on top, or once the inertia sort of starts to carry it, then it's not getting caught microscopically as much, and it takes a little bit less effort to keep it going across the carpet. So in the kinetic case, this frictional force is not called Fs, it's called Fk. This is a frictional force, but once the object is moving, it's called kinetic frictional force. Now in this case, notice that I have drawn the frictional force to be less than the pull, and that means the object can move. Because in all the previous cases, the pull was equal to the friction, the pull was equal to the friction, the pull was equal to the friction, until you get just higher than the maximum value allowed in the static case, in which case it breaks free, and now my pull is higher because the frictional kinetic frictional force is governed by this equation. There's a different coefficient here. So the kinetic frictional force is oftentimes less than the maximum static there. And so the pull that you were initially giving is enough to overcome it and to begin it sliding across. So we're pulling with more than the frictional force we have, and so the object's going to accelerate and move on to the right there. All right, so let's draw that in terms of a graph. Let's dive into this as deeply as we can go with some understanding that we're never going to understand everything about it, right? This is just a model, right? These equations of kinetic friction and stuff, it's really more complicated than that, but these equations work well to give us an approximation of what the frictional force will be, and we can use them in equations, but they're just a model. I mean, the real frictional force is not exactly equal to the weight times this coefficient. I mean, that's a simple equation. In real life, it's more complex. It's to 5 decimal places. That's probably not the frictional force, but it's good enough to solve a simple problem and get a good approximation of what's happening, okay? Now, on this graph, what we're going to do on this axis is we're going to put the tension in newtons. In other words, we're going to graph how hard we're pulling on this box. In other words, this tension right here. And what we're going to do is we're going to first, on this axis right here, we're going to graph the frictional force in newtons. All right? So I'm going to put here friction. This is friction. Now we know there's 2 regimes. There's static friction and kinetic friction. Now, let's talk about what happens, right? What's going to happen? Here, when I'm pulling with a tension on this rope of 0 newtons, then there's 0 frictional force. Well, how do I know that? Nothing's moving. So if I have a weight here, I do have a frictional force that cannot be bigger than this. But basically, if I don't pull on it, then there is no backwards frictional force here. So I guess what I'll do is I'll change this diagram. Maybe I should, maybe I'll draw another one over here. Let me draw another one over here to avoid any issues here. I'll draw another one, right? So here is the normal force. Here is the weight. Here is the rope I'm pulling on with some tension T. And I drew this to introduce the kinetic frictional force. So here there's the frictional force, and it can really be of 2 types. There's a static, and there's also a kinetic. And depending on which frictional force you're getting is if the object is moving or if the object is not moving, okay? So we'll refer to this drawing here instead of this one, because this one really went with the kinetic frictional force. All right, so when I'm not pulling at all, there's literally no frictional force. So I have 0 newtons here. But as I begin to pull on it, then with some force, then what happens is the frictional force begins to rise in a linear fashion, higher and higher and higher and higher. As I pull more and more and more and more and more newtons to the right, the frictional force gets bigger and bigger and bigger and bigger and bigger to exactly, I tried to draw this at a 45-degree angle. However many newtons I'm pulling to the right, the frictional force is rising in the reverse direction with exactly the same force. And this is what I was trying to illustrate over here. When I pull with this many newtons, like let's say it's 1 newton, then there's 1 newton of force in the other direction. How do I know? Because the object's still not moving. They have to be balanced. If I pull with 3 newtons, the frictional force in the reverse direction must be 3 newtons. How do I know? Because the object's not moving. If I pull with 6 newtons, then the object must be resisting with exactly 6 newtons. How do I know? Because the object is not moving, even in this case. But eventually I'm going to pull with a number such that the frictional force cannot exceed, because this static frictional force cannot get bigger than this number, the coefficient times the weight of the object, the normal force. It can't get bigger than that. So if I ever pull more than that, then since the static friction can't get bigger anymore, then what will happen is the object will start moving. And once it starts moving, everything's governed by this equation. Okay? So as I pull with a newton, the frictional force goes up by a newton. When I pull with another newton, then the frictional force goes up and up and up and up to exactly counteract it. And then what happens is eventually I hit some critical value of the frictional force, and this is called Fs max. That's what I wrote down on this board over here. I said eventually you reach a point where you cannot get a higher frictional force. That's the maximum value because it cannot get bigger than this number. And that is right here at the top. Eventually, if I keep pulling even more than that maximum frictional force, then what happens is the frictional force drops dramatically down, and then we continue along to the right at a lower value of a frictional force. And that lower value of the frictional force is called the kinetic frictional force. This is the kinetic frictional force right here. Now, believe me, I would not have drawn this picture on the board if it wasn't something I want you to think about, okay? So don't just like flush it and move on to the next thing. I want you to really try to understand what's going on here. It's not like rocket science, but it takes a little bit of thinking, okay? When the object is not moving, which by the way, is in this entire regime right here. So let me put a dotted line right here. In this regime, when I'm pulling from 0 newtons up to some value, here's some critical value, in which case I overcome the boxes, overcome and start to get it to move. The box is at rest, right? And over here in this region, as long as I pull bigger than that critical value, the box is in motion, right? So this was called static friction. And this was called kinetic friction. Now, you can see from the graph that even when the box is moving, there's still friction. This is a graph of the frictional force that's coming about from the carpet or whatever. There is still friction here. However, if I pull harder and harder and harder and harder, the kinetic friction stays constant. It doesn't go up or anything. It's like once you break it loose of its being stationary and get it moving, then the kinetic friction is a fixed number. It doesn't go up or down or change. It's just a number. And that's why when I break it and I start moving it and the box is in motion, then the kinetic friction is just a constant value. It would just be some constant drag over here. But before the box is moving, as I pull harder, the box is offering more and more and more resistance to my pulling, and that's what keeps it from moving in the first place. That's what makes it not move, because the forces are in balance. Eventually you reach that critical maximum value of the friction, in which case 1 nanonewton above that, and then it begins to move, and so on. And so what we have is when the box is at rest, the frictional force, which is called the static frictional force, has to be less than the coefficient of static friction times the normal force. But once the box begins moving, then the new frictional force is replaced by the kinetic frictional force, which is equal to the coefficient of kinetic friction times the normal force. Notice these equations look almost exactly the same, but this one has a less than sign and this one has an equal sign, because the static frictional force can change. It just keeps getting bigger as you pull more. all the way up until the point in which the object begins to move. That's why there's a less than sign. It means the static frictional force can get bigger, 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 bigger dynamically as I pull more until I reach the breaking point, in which case it stays fixed. It doesn't, the frictional force changes to the kinetic friction and then it stays fixed. So if the frictional force is less than this value here, and if the frictional force is equal to this value right here, then right at this interface right here, the frictional force is equal to this right here. So it's the coefficient of static friction times the weight of the object, or the normal force. It's less than this critical number right at the breaking point, then the maximum amount of the friction that can be kind of like generated by the object, so to speak, or resisted by the object, is equal to the coefficient of static friction times the weight. And then once you get just a little bit beyond that, even just a nanonewton pull extra, then the friction drops dramatically lower to a new value, which we call the kinetic friction here. All right, that's a lot of talking. I hope I've made it clear. Now, I know that none of this will be clear until you solve a real problem. And that's what we're going to do right now. But just before we do that problem, go back to these equations, which I wrote down early on in the lesson. And now that we've drawn the pictures and we've done all these things, they should make more sense to you. The static frictional force is a force that can change. It is a force that can start at 0, which is no friction at all, up to and including a maximum number. Well, this maximum number is the weight of the object times some coefficient based on the surface you're on. But as long as the object's not moving, if I pull harder and harder and harder, the static frictional force gets bigger and bigger and bigger and bigger to keep it in balance, and so the object isn't moving. But at some critical moment, the static frictional force gets to that critical value that is the maximum amount of static friction it can offer based on its weight and the object it's sitting on. That is the critical value beyond which the object will start to move. And as soon as you get to pull a little bit harder than that, you overcome the static friction, the object begins to move, the object also becomes a little easier to keep moving, and the friction suddenly drops down to the kinetic friction. And the kinetic friction looks the same, but it's a different coefficient, again, times the weight. All right. That, again, was a lot of talking. I think this will be a little bit easier once we can get a few problems under our belt. I promise it's not difficult, but I did want to explain where it all comes from. Draw some pictures so that you can really feel it in your bones, what's going on here, okay? So here we go, problem number 1. A box of fresh bananas weighs 40.00 newtons and is sitting at rest on the floor in the back of a store. If the coefficient of static friction between the material of the box and the floor of the room is 0.400 newtons, and the coefficient of kinetic friction between the two surfaces is 0.200, then we have 4 parts. I'm just going to read the first part. We'll solve that part first. What is the magnitude of the force of friction while the box is sitting stationary, subject to 0 horizontal forces? So the first part is saying, okay, what's the frictional force when nobody's pulling or pushing on the box at all? I think you already know the answer, but before we say it out loud, let's just write a few things on the board and draw a quick picture. So what we have in this situation right here is, first of all, what we want to do is we want to write down the coefficient of static and kinetic friction. The coefficient of static friction between the box and the floor is 0.400. The coefficient of kinetic friction is 0.200. Okay? Notice that the coefficient of static friction is bigger than the coefficient of kinetic friction, and that also lines up with what we said, because we said that once the object starts moving, the frictional force jumps down, and that's because most of the time the kinetic frictional coefficient is less than the static frictional coefficient. So the force that comes about from friction is less than the maximum that the static friction can reach. Okay? So in the problem, that comes about with the numbers that we have here. Now let's draw a picture. What happens? We have a box, right? And this box has it says it weighs 40 newtons, so we can go ahead and just do that. The weight is 40 newtons. Now, just to be totally clear, this box is sitting on a floor, and what is the normal force acting up from the floor, pushing up to the box? Well, the normal force is 40 newtons, because it has to be equal and opposite to the weight. All right. Now what we're saying is that what is the magnitude of the force of friction while the box is sitting stationary with 0 net horizontal forces, or zero forces acting on the object, okay? Or zero pushing or pulling on the object. What we're basically saying here is that in case number 1, there is a force acting to the right of 0 newtons. In other words, I'm not pushing it at all. And so that means that the reaction, the frictional force that comes about, we're going to call it Fs, also has to be 0 newtons, because everything has to be in balance. If I put a different number here, I guess I'll put a slash through that to tell you that's 0 newtons. Everything has to be in balance. Up has to balance down, right has to balance left, otherwise the box is moving. So the frictional force, the static frictional force, is 0 newtons. When you don't push on an object, there is no friction pushing back, right? Because if there was something pushing when you weren't pushing, then the thing would be moving. But it's not moving, so everything has to be balanced. All right, take a look at part B. What is the magnitude of the frictional force when a worker applies a positive horizontal force of 6.00 newtons? What's the magnitude of the frictional force when a worker applies a positive horizontal force of 6 newtons? All right, so let's go and figure that out. So let's go to part B. What we're basically saying is that for part B, we have the box yet again, and we can do the first part the same. The weight is 40 newtons. The normal force is 40 newtons. But in this case, somebody walks over and grabs a rope and pulls on it to the right with a magnitude of 6.00 newtons to the right. It even says positive force, horizontal force, F sub x of 6 newtons. So my question to you is, if somebody pulls on it with 6 newtons, what kind of frictional force are we going to get as a result of that? Well, what we need to do is go back. We have a static force and we have a kinetic frictional force, right? The static friction that can come about has to be less than or equal to the static coefficient of static friction times the normal force. That's what we wrote down up here. So first you consider the case to see, is it stationary or not? Okay, let's see. The maximum static frictional force is going to be equal to this, which is exactly what I wrote down right here. So it's going to be less than or equal to the static coefficient of static friction, 0.400, times the normal force, which is, normal force is 40 newtons. That's exactly equal and opposite of the weight, so 40 newtons. All right, now when we carry out this calculation, what we get when we multiply this times this is we're going to get less than or equal to 16 newtons. So what is this telling us? This is telling us is that for this problem, when a 40 Newton box is sitting on a surface where the coefficient of static friction is 0.4 like this, then the maximum static friction force that can be supplied by the contact forces of the friction there before it begins to move, the maximum counterforce, for lack of a better word, the frictional force, is limited to 16 newtons. But in this case, I'm not pulling with 16 newtons, I'm pulling with only 6 newtons. So because the 6 newtons of pull I have is less than 16 newtons, I know that we're in the static case. In other words, we know the box isn't moving because the frictional force that can be supplied can go up to a maximum value of 16. But I'm only pulling with a value to the right of 6. And that means that the static frictional force will go in the other place, 6.00 newtons, to balance it out. And this thing is going to remain static. So in this case, the static frictional force is going to actually be equal to 6 newtons. Now, since we've done this, let's go back to our graph and just make sure it makes sense. Remember what the graph says. The graph says is that when a box is sitting stationary at rest in the ground due to friction, as I pull harder and harder and harder, the friction force rises and rises and rises so that the box stays stationary even as I'm pulling more until I hit a critical maximum value. This critical maximum value of the static friction is governed by this equation. So all we did in this case is we used the actual static friction coefficient and the actual weight to calculate the maximum static frictional force that can be supplied. So that means on this box, if I pull 6 newtons, then friction is going to counterbalance with 6 newtons of force. If I pull with 7 newtons, then it'll counterbalance with 7 newtons. It'll dynamically resist me more because, again, as you push on a box harder and harder and harder, you know that it doesn't move until you reach a critical value, right? Sometimes you have to push really, really hard to get the box moving. In this case, the static friction can supply up to 16 newtons of friction before it begins to move. So I would be able to pull this at exactly 16 newtons before it would begin to move. Any force I pull on it less than that will mean the box won't move. That means the friction force for the 6 Newton force is got to be 6 newtons in the opposite direction. If I do 8 newtons, it's going to resist with 8 newtons. 10 newtons, it's going to resist with 10 newtons. And then when I get to 16, it'll barely resist, and then 16.01 newtons, it'll break free and start sliding. Okay, that is how we do these problems. You calculate the maximum static frictional force, and you see if you're pulling on it less than that. And if you are, then you know the box isn't moving, and that's what we have done here. All right, now let's read part number 3. What is the minimum amount of force needed to be applied to the box of bananas for it to begin moving? We basically just talked about the answer, just in passing there. But since we know that the static frictional force is less than or equal to 16 newtons, right? Then what we know is basically that the pull in the x direction, let me put a capital F here. The capital F in the x direction, the pull force that I'm pulling to the right at a minimum must be equal to 16 newtons, because that is the maximum frictional force. The question was, what is the minimum amount of force needed to be applied? So anything 16 newtons or higher, the box will slide, right? Because in that case, and we'll draw a quick little picture here, right? We have the weight, 40 newtons. We have the normal force, 40 newtons. And here we're applying 16 newtons, and in this case, the frictional force can be 16 newtons, but it cannot be higher than 16 newtons, because this equation for the coefficient of static friction, it only means that it can be less than or equal to this. It cannot be bigger than, in this case, 16 newtons. So if I pull with 16 newtons, it can resist with 16 newtons, and the question itself says, what is the minimum amount of force needed to be applied to the box? 16 newtons is the breaking point. Technically, it would be 16.0001. 1 little nanonewton higher will begin to move. So we just put 16 newtons, but you really know that because of the equality sign, that it's just a smidge more than that is really going to get the box to move. Okay. Now the last question says, what is the minimum amount of force needed to be applied to the box to keep it moving at a constant velocity? What is the force needed to be applied to the box to get it to be moving at a constant velocity? So what we figured out here is that essentially, we can apply a force pulling to the right of 16 newtons to resist the maximum static friction of 16 newtons before it begins to move. So we pull and we pull and we pull. We finally get to 16.0001 newtons, and then the box begins to get dislodged and begins to move. At that moment, the equation of static friction does not apply anymore because the box is moving. So as soon as the box breaks free and begins to move, this does not apply anymore at all. And we showed that in our graph when we said this equation applied here. Once it's moving, this new equation applies here. So let's calculate the kinetic frictional force once the object is moving. So the kinetic frictional force, once the object is moving, is the coefficient of kinetic friction times the weight of the object, or the normal force. So the kinetic frictional force is, what is the coefficient of kinetic friction? It's 0.200. What is the normal force? So the weight is 40 newtons. Okay. What you'll get is 8 newtons. What does this mean? This means that what we have is the situation of the box moving. We have, again, the weight acting down, 40 newtons. We have the normal force acting up, 40 newtons. But what's going on is, remember we said, is that we push an object, it's really, really hard, but then once it starts moving, it's like easier to get it to move, or to get it to continue to move. And that's reflected in our graph because the frictional force drops down, and of course that means it's easier to push once the thing starts moving. And once the thing starts moving, the kinetic frictional equation applies, which only has 8 newtons of friction here. So that means the frictional force right here is 8 newtons. And it's a fixed number. It doesn't change or go up or go down. Once the object just starts moving, the kinetic frictional force is a constant. It's fixed. In this case, it's 8 newtons. It's based on the coefficient of kinetic friction and the weight of the object, or the normal force. So the question here says, what's the minimum amount of force needed to be applied to the box of bananas to keep it moving at constant velocity? Well, you need to, the minimum force means you need 8 newtons in this direction. right? Because if it was moving and it was already starting to slide, if you then applied exactly equal and opposite to the frictional force, then it would continue to move to the right at constant velocity. So we would say that the force in the x direction, the minimum, is going to be 8.0 newtons. So let's talk through this problem really quickly, A, B, C, and D, since we kind of had to do a lot of back and forth and just make sure we get it all and have it all in one place, okay? Part A basically said, what is the magnitude of the frictional force when the box is sitting there with no net forces, with no force pushing on it, basically? Well, when there's no force pushing on the right, there's no frictional force at all. And so everything's balanced. It has to be 0 and 0, and so the frictional force is 0. Second part of the problem, what's the magnitude of the friction force when a worker applies a positive horizontal force of 6 newtons? What we did is we calculated the maximum frictional force that can be supplied or resisted in this situation, which is 16 newtons. We're applying a force less than 16 newtons. So what's going to happen is the frictional force is going to rise to meet however much we're pulling so that the box doesn't move. And so we pull to the right with 6 newtons. The frictional force is 6 newtons in the other direction. 6 is less than 16, so we're still in the static case. 16 is the critical number beyond which we're pulling it so much that it's going to start moving. The third problem says, what's the minimum force needed to apply to this box for it to begin moving? Well, we remember that 16 newtons is the maximum critical value of the static friction, so the minimum force required in the other direction has to be 16 newtons. That's the critical value to get it to move. Now, really, it's going to be probably, like I said, 16.00001 or something newtons, just beyond the threshold. That'll get it to start moving, but we just write 16 there. And then what is the minimum amount needed to apply to the box of bananas to keep it moving at constant velocity? So once we pull with 16 newtons, the box starts sliding, and then the friction is no longer 6 newtons anymore. It drops, and the coefficient of kinetic friction applies. We calculate the coefficient of kinetic friction of 8 newtons. That means that the sliding friction, once it's moving, is now only 8 newtons. We were pulling with 16 and it wasn't moving, but we just got it going, and then suddenly the friction force drops to 8 newtons. So then we have to apply a forward force of only 8 newtons to keep it moving at a constant velocity there, because then both forces will be balanced and it will still be sliding along with whatever velocity when you broke it free it started sliding at. Will keep moving at that speed. All right. And so, of course, if I pull more than 8 newtons, this 8 newtons is going to stay the same. Like if I pulled, let's say, once it starts sliding, let's say I pull with 20 newtons of force. So once the box starts sliding, I really start pulling. Okay. Well, then the right-hand force would be much bigger than 8. I would have a net force in the x direction because of Newton's law, right? And so I would have an acceleration. I would have a net force. So it means since F equals ma, I'd have to have an acceleration. When I apply the same force as the backward friction, then I get no acceleration, just moving at a constant velocity, right? If I pull more than 8 newtons, I'll have a net force in the x direction. The thing will then speed up, essentially. Now that's a lot of talking. Believe me, I wouldn't have drawn this graph if I didn't think it helped illuminate the situation. I would not have drawn these pictures in the beginning of static friction. Static friction causes a lot of people trouble because it's kind of hard for us to visualize how, when I push on something, how it can push back as I increase my push. How does it know, quote unquote, to push back? It doesn't know anything. It's basically action and reaction forces. Every action is an equal and opposite reaction. And when these things are sliding on the ground and the hooks and the valleys and the crevices are catching down there, that's what's applying the counter push back. It's the literal touching down there in the microscopic that we talked about before. So watch this a few times and then follow me on to the next several problems where we'll incorporate kinetic friction and static friction into all of our analysis of Newton's laws of motion to see how things move when friction is involved. Learn anything at mathandscience.com.